Okay, welcome everyone to this week's Physics Meets ML. We are very happy to have Gur-Ari from Google Research and the Blue Shift team here today. So Guy did his PhD at the Weizmann Institute in Israel in 2014, and he then did postdocs at Stanford and the IIS in Princeton, and then turned into machine learning and tried to use physics, or is trying to use physics to explain aspects of deep learning. And but today he's telling us about the inverse direction, namely using machine learning, in particular large language models, to do physics. And we are very excited to hear about this recent work, Minerva, which is being used to do physics. So yes, that's all I have to say. So the floor is yours, Guy, and yeah, please take it away.
Yeah, thank you very much for the invitation and the introduction. Very happy to be here. And I'll tell you today about Minerva, a model that can do math and science questions that around a high school level, maybe early college level difficulty. Feel free to stop me if there are any questions along the way. Let me start with a very brief review of transformer-based language models, just to remind you of the basic facts about these models that we'll use throughout this talk. And again, if anything is unclear, feel free to ask. So the basic setup we have with language models is that we have a model that accepts a sequence of tokens as input, and I'll use that I'll use that term tokens throughout the talk. Token here just means roughly you take your sequence of characters and you chop it up in some sensible semantic way. So a token could correspond to a single word, or to an English, or to a single digit, or to a single symbol. This tokenization step is learned. We won't worry too much about it. So just know that when I say tokens, I mean some basic semantic unit of text. If it's more convenient, you can think of tokens as just characters, because we could in principle do that as well. So the model accepts a sequence of tokens, which represents some text that we want the model to take as input. And then the model's output is a probability distribution over what it thinks the next token should be. So that's the model's basic task: accept a series of tokens as input and try to predict the next token probabilistically. We can do that with many different kinds of models. Here we're going to focus on transformers. And with transformers, the basic architecture is what's shown on the right. So we accept the text or the series of tokens as inputs. There's also something related to the positional embeddings that I won't get into here. And then we have a series of layers, as always with deep learning. The special thing about transformers is that some of these layers are what's called self-attention, which I'll explain in a minute what that layer consists of, but it's some deep learning layer. And then we have alternating self-attention layers and feed-forward or ordinary fully connected layers. We have some other components going on here. There's layer normalization and skip connection, but I won't get into that. The main thing to remember is that we have these alternating attention and fully connected layers repeated again and again, until at the end, in this talk, we're going to ask the model to do text prediction, meaning we're going to try to get it to predict the next token. And I think, so just to make sure that the basic setup is clear, we have a sequence of tokens going into the model. It gets processed by these layers. The attention layers can do essentially two-body interactions between the different tokens, as I'll explain in a second. And then the feed-forward layers take each token, which is represented internally as a vector, and act on it using a fully connected, just a normal fully connected layer. And they do it separately on the different tokens. So that's the basic architecture. In a bit more detail about what happens in that attention layer, essentially what the attention layer does is for every token in our sequence, so let's look at this token, for example, it calculates a mask over all the previous tokens, or a set of weights over all the previous tokens, which tell the model which of the previous tokens are the most relevant ones or the most salient ones to make a better prediction about the current token. And it's backward looking, and the models will be looking at, it's all backward looking. So every token looks at all the previous tokens, calculates a mask over them. This is all learned with some weights, and then calculates a weighted average over those, takes the values in those tokens and takes the learned mask and just calculates a weighted average. And this is what's used to update the value of the token. And it does this again and again. So let's say this is the input, this is some hidden layer, and we're going to calculate attention by attending to all the previous tokens, update the value, and we do that again and again. Or each one of these would be an attention layer. So that's at a very high level what attention does. And then a couple more facts about transformer-based language models that will be useful to remember in this talk. First is the way we train them. There are a few different ways to train these models. What we're going to do here is kind of the simplest thing, which is autoregressive training. We said that a model takes as input a token sequence, and it outputs a prediction about the next token. And so what we do to train these models is we take a bunch of documents containing text, could be general text, or as we'll see in this talk, could be mathematical text or whatever it is. And we look at let's say every substring starting at the beginning of the document, every substring of text in this document. We say, here's the input up to this point, try to predict the next token. And then we use as target the actual next token that was in that document. And we do gradient descent on this signal using cross entropy loss. And so if we have a document with n tokens, we turn that into n different samples, n different targets on which we're training the model. And we do that on a bunch of documents. So that's how we train the model, by trying to predict the next token. And then we can use this model for doing different things. In this talk, we're going to use it for text generation. So we can use this model, we prompt it with a certain input, and then we ask it to complete the input, to keep generating text that sort of is the likeliest text given what it's already seen. And the way we do that is, okay, given the input, we ask the model to calculate the next token prediction, the distribution, the probability distribution for the next token, and then we sample from that with temperature. And so by this, I mean, the model gives us, given the input, it gives us the probabilities Pi for the next token. We choose some temperature T, and then we sort of renormalize all of our temperatures using temperature T. This is standard temperature sampling, and then we sample from this updated distribution. And the point of doing that is that this temperature gives us a control over the trade-off between model accuracy and diversity in the answers we get. If we set the temperature very low, let's say we set the temperature to 0, that means we are always going to pick the next token that the model thinks is most likely. So we will get what the model thinks is the most accurate answer, but at the cost of some diversity in our answers. And you'll see later on in the talk why diversity is important. If we set the temperature very high, then we'll be sampling from the tail of the distribution. We'll get very unlikely tokens, which means the accuracy will probably be lower, but we'll get much more diverse answers. So we have this hyperparameter temperature that helps us make this trade-off. So that's how we sample a single token. Then to keep sampling, or to keep generating text, we add this token to the input. Now we have a new input that has n+1 tokens, and we do the same. Given this input, we ask the model to predict next token distribution, sample again and again. So text generation, I'll also use the word inference to refer to this process. And one thing I want to mention, just as a side note, is that there is a big difference in the actual efficiency of these two things, the training and the text generation. When we do training, we can do what's called teacher forcing. That means that we don't actually have to chop up the document to every substring and separately ask the model to make the next token prediction with a forward pass. We can actually do a whole document. We can ask the model for predictions on a whole document in parallel. And the technical reason why that happens is this causal mask that I showed before. The fact that the model only attends backwards in the sequence means that it can sort of in one fell swoop give us the predictions for all the tokens in a document, and then we train on all of those in parallel. So training transformers is very efficient compared to, let's say, something like an RNN, like an LSTM, for example. You have to do it token by token. But text generation is not that efficient because in order to get to the second token, we first have to sample the first token. We can't just look at the probability distribution of that. We have to do the sampling, which is a discrete step. And so when we do text generation, we actually have to do it token by token. And so that can get pretty slow, especially with the large models. So that's the background on transformers. And now I want to walk through a basic observation that has come up in recent years about these models. And this is the lesson that scale helps. Scaling up these models, both in terms of compute, so number of parameters, and in terms of how much data we're training them on, leads to better results. In many cases, it leads to predictably better results. Before I explain this graph, I just want to explain what it means to scale up compute for these models. So if we go back to the architecture, as you can imagine, there are lots of weights, lots of weight matrices going on here. So for example, feed-forward layers, of course, have weight matrices that are learned. And so one parameter that we use to, one hyperparameter that we use to control the number of tunable parameters in the model is the width of these fully connected layers, right? How many neurons there are in these layers. So that's one parameter we can control. Another parameter to scale up the model is the number of layers in the model. We can just keep adding layers, and so we'll get a bigger model. Attention also comes with its own set of internal dimensions, which are parameters we can control to make the model bigger. And so there are many different hyperparameters here that we can scale up. It turns out that it doesn't matter too much how we scale them up, as long as we keep the ratios kind of reasonable. To get the benefit of bigger models that I'll explain, we just kind of need to scale them all up more or less together without paying too much attention on keeping exact ratios fixed. And so this is the result that came out a couple of years ago from Jared Kaplan and Sam McCandlish and others at OpenAI, which showed that, yes, if you scale up these language models, making them bigger, training them on more data, you get predictably better results. So what's being shown here are these are training curves of a bunch of language models. Each line corresponds to a model at a certain size, at a certain number of parameters. And then the x-axis is how much compute, how many floating point operations in practice were used to train the model up to that point. And so again, every line here is, you can see the model as we start training it, it starts getting better, performance improves, and then at some point there's a knee and it starts kind of plateauing. It still improves, but more slowly.
Hey, Guy, can I ask a question? Sorry.
Yeah, yeah, please.
Great talk so far. I have a kind of remedial question. Is there some form of uncertainty quantification here? And if so, how does that scale with size?
Are you asking about a trained model, like how calibrated it is, like how good its predictions are?
Yeah, how good are its predictions, and does it know when its predictions are bad and that sort of thing?
Yes.
How does that scale?
Yes, so that turns out to scale quite well if you ask it in the right way. There's actually a recent paper about this. It really depends on how you ask it, how you try to measure the uncertainty. Because with these models, so if you have a vision model, you have your inputs, which are pixels, and let's say you do image classification. You have your inputs, and then your outputs are a probability distribution, and you can check the calibration on that, and that's what you have. But with text models, you can ask it the question, or you can ask it to solve a question in many different ways. So for example, it turns out that, let's say we want to measure the calibration on multiple choice questions. We can show it the multiple choice question, and then we can ask it, what is the answer? Let's say the choices are labeled A, B, C, D. We can ask it, what is the answer to this question? And then we can score the probabilities of the model on A, B, C, and D. If we do this, it turns out the large models are very well calibrated. If instead we ask it, what is the answer, and we score the text of the answer, that's not well calibrated at all. To a human, this wouldn't matter, but to a model, even the large models, it does matter a lot how we ask the question. So the bottom line is, There is a natural setting where these models are very well calibrated, at least on multiple choice questions, if we just asked it to score A, B, C, D for like an A, B, C, D multiple choice question. So it seems the models are well calibrated, but it's not always easy to get that calibration out of them, if that makes sense.
Yeah, great, thank you.
Yep. Okay, so back to this plot, we have these different training curves. And so the observation here is that for a given compute, we can find the minimum loss that we obtain. So sorry, the y-axis here is the test loss, the cross entropy loss on a held out set of data. The loss is again just computed on next token prediction. For a given compute, we can find the minimal loss and we pass a line through that, and we find that this line obeys a very nice power law over many different orders of magnitude. And then since then, bigger models have been trained and the line keeps holding. We don't see any signs of plateau yet. So scaling up helps. We also see it help with the quality of the model. Here's another example. This is not from language modeling, but this is from image generation, where again, transformer-like models are used, but it's a different setting, different algorithm, but still we can see qualitatively how scale can help. So this particular model, it's called Party. It's similar to DALL-E from OpenAI, and it's similar to Imagen from Google. This is a model that you prompt with some text, and then it tries to generate an image that matches that text. So here, for example, it was prompted with a portrait photo of a kangaroo. It's wearing an orange hoodie, blue sunglasses, standing on grass in front of the Sydney Opera House, holding a sign, and the sign says, "Welcome, friends." And you can see how the quality changes as you scale up the model. If you start with a model that has 350 million parameters, which is not small by any means, but you can see that the quality you get is so-so. It kind of matches what's going on here, but it's not clear that this building is Sydney Opera House, and the text is kind of garbled and so on. As you scale up, you need to scale up about 2 orders of magnitude to their biggest model, 20 billion parameters. And this does a great job. It captures Sydney Opera House. The text is legible. This picture looks like it matches the text quite well. So, and we see that with language models as well. Beyond the graphs, we can just see as we're interacting with these models that scaling them up just leads to much better results overall. And so this brings us now to the focus of this talk, which is, can we apply language models to quantitative reasoning problems? So we know that large language models work well on different tasks. We've seen them work well on natural language. We know that they also work well on code. So in the work in the Codex model from OpenAI, and we've seen that also at Google with Palm Coder and DeepMind have AlphaCode. We've seen that in many cases now where you take these language models, same architecture, same everything, but you just, instead of training them on general language, you train them on code. You take a lot of code, let's say from GitHub, you show the model a bunch of code and ask it to predict the next token, and you do that on all the code you can get your hands on, and you get a model that's really good at basically doing autocomplete. You can give the model let's say a documentation of a function, and if the function is simple enough, it will just write it for you. And there are many other cases where we've seen these things work, and again, improve with scale. And so for us, the question was, will the same thing work on math, science, and other quantitative reasoning questions where you kind of have to take a question and, at least as a human, try to understand what's going on there, break it down into multiple steps, work through the steps, and sort of get to an answer? Can we just do all that by taking a big model, training it on lots of data, and see what we get? And so this was our approach in this project. First, we collected a large data set of documents that contain math. I think this is kind of the key step here, which is we want to go after math and science questions. We can't hand design a large data set that does that. So we have to go out and get the data somehow. But we know that just scraping the internet is not going to do it, because the current models we have, they're not very good at solving math and science questions. So what we do instead is we do some filtering to get the kinds of documents that are relevant for this domain. It's still going to be a very large data set. And then we're going to go and take a large model. We're going to train it. We started with a pre-trained model, and then we fine-tune it on this data set, as I'll explain. And then the last step is, once we have the data set, once we have the trained model, there are a bunch of different inference time techniques that we can apply to improve the quality of the model. So these are things that we do without touching the weights of the model, just by being more clever about how we sample answers from the model. And I'll explain all the techniques that we used in detail. So before going into the details of how we collected the data and trained the model and so on, I want to show a couple of examples just to give a sense of what you can get if you train a large language model with lots of relevant math-related data that was essentially scraped from the internet. So here are a couple of examples. This first example is from a data set called MMLU, massively multitask language understanding benchmark. It covers a wide variety of topics. These are all, excuse me, multiple choice questions. We're focusing on the STEM part of this benchmark. So this will be one benchmark that we'll use a lot in this talk. So let me just go through the question here. We have a uniform solid disk. It rolls down an inclined plane without slipping. And then the question is, after some time, what fraction of the disk's total kinetic energy is rotational kinetic energy? Okay, so we need to calculate the rotational energy, and we need to calculate the translational energy, and then sum and calculate the ratio, basically. And then this is a multiple choice benchmark, so we have these few ratios to pick from. And then below is what Minerva, what the model generates as a response to this question. And it generates this in LaTeX form, as I'll explain in a minute. All right, so it says, okay, the disk has these two different kinds of energy. It introduces a few symbols for the speed and the moment of inertia and so on. It writes down the formula for the kinetic energy. And then it writes down the formula for the rotational energy. And then it plugs in the formula for the moment of inertia for a solid disk. That's happening here, simplifies, and then it says, okay, therefore the ratio is, and so here's the ratio that it wants to compute, plugs in the stuff from above, simplifies, gets the 1/3, and then picks out the answer, which is B, which is 1/3. And the way this answer is generated is just as I described before. The model gets the question as input, and then we ask it to predict the probability distribution for the next token. We sample from it and we get D. And then we add that to the input, we sample again, we get disk. And then when we get to the math part, this is all generated in LaTeX, including the dollar signs or begin equation and all that. These are all tokens that the model generates one by one. So we take this LaTeX input, LaTeX output, and then we render it. So it looks like this. But the model, for the model, this is all LaTeX input and LaTeX output. So that's one example from the model. You can see this in other examples. We have them online in the Minerva Sample Explorer. And here's another example from the second benchmark that we'll focus on in this talk. This is called math. So these are math questions at a high school competition level, roughly. And again, they have a few different topics: algebra, pre-calculus, number theory, a few topics like that. This question is from intermediate algebra. And so again, we have a question, find the center of the ellipse whose equation is given here. And this is the model output. So it writes down the equation, and then it goes through a few steps where it completes the square, simplifies, and then ends up with this form. And then it reads off the center. Okay, the center of the ellipse is -4, 1 from this final form. And again, this is all generated like token by token, including the LaTeX arrows and the new lines and so on. So this is kind of where we are at now with these models. That's roughly the level of questions that these models can solve. And I'll show a bunch more examples as we go through the talk. Any questions so far? Or if not, I'll get into the details of how we train the model and how we do inference with them.
How do the fail cases look like?
I will show examples of fail cases. Yeah, good question. I have a bunch of slides on mistakes that the model makes.
Sorry to interrupt again, Guy, but I'm trying to wrap my head around how, if it's asked to do the next token, which is like a symbol, like a dollar sign in LaTeX or something. I mean, it must have a bigger plan in mind for how it's going to present the proof. Or, I mean, that's a very vague way of asking my question, but how is it working that it's asked to just predict the next token without being asked to predict sort of the concept of the solution or something, if that question makes any sense?
I don't have an answer to that because I don't know how it's doing it really. The thing I can say that what helps it generate this is the fact that we prompt it with a few sort of training examples that include a full solution. As I'll explain, I'll show you exactly what that looks like. But we put in the input, we put a few question answer pairs from the training set, nothing from the test set that we're checking on. But we have a few examples of things that kind of look like this. And it turns out that once you do that, and then you ask it a new question, it prompts the model to try and answer that question in the same kind of way, in the sense that it also generates a step-by-step solution. But everything beyond that, how does it actually kind of know where it's going with this? I don't know. I don't have an answer to that. This is all, this is kind of the black box part of these models where we don't really know how they actually do the thing that they do.
Okay, but you don't ever ask it to give a probability for some set of symbols, like give the next equation or something. You really just ask it the next symbol.
Yes, just the next symbol. Yeah, just the next symbol.
Okay, thanks.
Yep.
And another question would be where how large are the data sets, like these math intermediate algebra set and
how many questions are in this?
Yeah, roughly.
Yeah, I think it's in the thousands, a few thousands on the test set is the size of math. And I think MMLU is similar, I think.
Okay.
Yeah. Okay, so let me get into the details of how we collected the data and how we trained them all. So the key ingredient here is the training data set. So we have, in this data set, we have 60 gigabytes of documents that contain natural language intermixed with mathematical expressions. And these come from two sources, which are of roughly, they're mixed with equal importance when we train the data, when you train the model, sorry. So the first source is archive papers. We have a snapshot of archive from, I think, about a year ago. And we take all the source files from the archive and basically present them as is to the model. So every archive paper becomes a document, and we do next token prediction on this document, and we do that on all the archive papers. And then the second source is web pages that contain mathematical expressions. So we take scrape web pages and we filter them down to those that actually contain math in them. So this is typically in the form of MathJax, this plugin that lets you write LaTeX and render it online. And then we process these web pages. We remove the HTML tags that surround the LaTeX, and we just leave the text and the LaTeX there. So the end result of processing these web pages looks pretty similar to archive papers. You have, in the sense that you have natural language, and then you have LaTeX expressions and natural language, and so on, just without all the HTML tags. And that's it. That was kind of the trick, I would say, of getting this to work, is to say, okay, we want to go after quantitative reasoning. Again, we can't hand design a 60 gigabytes of data ourselves on like what it means to go after quantitative reasoning. So we'll try to filter the data that we do have to kind of get at this problem and hope that it works. And so the end result is at least we get a model that knows not only natural language, but also knows tech. And as we'll see, it has also a couple of other tricks. So that's training data set. And so we take that, and then we train a few models. So in this project, we started with pre-trained models that were trained on natural language and some code. These are called Pathways Language Models, or PaLM for short. These were released or the paper was released by Google some time ago. There are 3 scales that these models were trained on, with 8 billion parameters, 62 billion, and the largest had 540 billion parameters. We took these 3 and we fine-tuned them on this technical math data set that I just described. And those are the Minerva models. Those are the models that we were working with. And to give a sense of how much compute is needed to do this, For the largest model, the 540 billion parameter model, this was trained for about a month on about 1,000 TPU chips. The smaller models were trained for less, about I think about 2 weeks for about 500 chips, something like that. So that's kind of the scale. And this was enough to cover about one epoch, roughly one epoch of the data. Okay, so that's the model. So we collected this math data set. We took pre-trained existing models. We didn't change the architecture. We didn't change the optimization. We used the same autoregressive objective for next token prediction, and we fine-tuned the model. So now we have these models, and they do okay. You'll see results of what these models actually do without any other interventions. But there are a few techniques that we can apply at inference time that dramatically improve the quality and performance of these models. So that's what I'll describe now. I'll go one by one on each of these interventions that we do at inference time. And in the end, you'll see some ablation of how some of these techniques help. So the basic technique that we have for improving question answer performance is few shot prompting. And this was noticed in the GPT-3 paper. It was noticed that with these large language models, as I already mentioned before, it really helps to show them in the input some question answer examples before that are similar to the question we're going to ask. That really increases the probability that they'll get the answer right. So this is, for example, the prompt that we use when we ask the model arithmetic questions. We use the same prompt for all arithmetic questions. It's just enough somehow for the model to see a few examples before it's actually asked the question. So you can see it's in this format. The exact format doesn't actually matter. Q, what is 12 plus 34, A 46, we have a few of these. We put that in the input, and then we add Q with the actual question we want to ask, and then we generate the answer. So that's the whole story with few shot prompting. And that helps a lot. The next thing that helps is building on few shot prompting is what's called chain of thought prompting. This is where we don't just, so if we do few shot prompting like here, and then we ask them all another question, it will try to just spit out the answer without any intermediate steps, and it will do as well as it can. This kind of works fine for arithmetic, but for anything more complicated, this doesn't work because the model can't just solve a complicated math question in one pass through the network. We want to get it to somehow break it down to multiple steps, solve them one by one, and so on. And the way we can get it to do that is through chain of thought prompting, where, again, we're prompting the model with a few questions, but we don't just give it the answer, the final answer. We give it in the prompt a step-by-step solution to that answer, and then we get to the final answer. So this is, for example, when we ask it questions from math, we use a prompt that includes 4 examples, and this is the first one. It's just one of the examples from the training set with its solution. So find the domain of this expression, and so this is the solution. The expressions inside each square root must be non-negative, so there are a bunch of inequalities and so on. And at the end, the final answer is that this is the domain of the expression. So we have 3 more examples similar to this from the math data set. And whenever we ask them all a question from math, we show it this prompt, and then we ask it the question, and that causes it to try to generate a step-by-step solution and then get to the final answer and then say, I hope it is correct, because this was in the prompt. This technique helps a lot with the more complicated questions. It has a long history it goes back to 2017. Back then they called these rationales, and they used fine-tuning and not few shot. And then the most recent paper from Wei and company, what they really showed is that if you take natural language prompts and you do it with few shot prompting, like here, you don't train them all on them, but you just do few shot prompting, that can boost performance by a lot. And we use that technique in all our evaluations. And then the kind of last inference time technique that we use is what I'll call majority voting, or sometimes it's called self-consistency. And here the idea is as we said, we can sample from these models with temperature. So if we want to get the model to just give us the answer it thinks is most likely, then we will sample with temperature 0 and we'll get the same thing every time. It's not probabilistic anymore, it's just kind of greedy sampling. But if we sample with finite temperature, then every time we sample, we'll get a different answer. And it's not just that the final answer will be different, the whole chain of thought will be different as well, because we prompted it with chain of thought. And it turns out that there is signal there that we can actually use to improve the performance of the model and improve its accuracy on the final answer. And the idea is, instead of sampling once, we sample a bunch of times with some temperature. So we have a bunch of chain of thoughts like this, and then we get the final answers, which are short. We bucket them, and then we just choose the bucket with the most common final answer. So it's sort of like we're letting the model vote on what the best final answer is. This, as you'll see in many cases, this improves performance dramatically. And intuitively, the reason this seems to work is that there's only one correct final answer, but there are many potential wrong final answers. And when the model gets it wrong, it kind of gets distributed among these many different wrong final answers. So by allowing it to kind of dilute the signal of the wrong final answers, it implicitly boosts the signal of the correct final answer. That's a very hand-wavy explanation, but you can see in practice how this is kind of a trade-off between the entropy of all the different final answers and the accuracy that it actually gets on the final answer, if that makes sense. At the end of the day, this is the technique we use. We need to sample an order of 100 times from the model to get a good signal, and this helps. So these are all the inference time techniques that we use. There's one more thing that we do just to improve our estimate of the actual accuracy of the model, and that is that we need to normalize the final answers. And that's because in these questions, there are many different ways to present the same final answer. For example, if it's a question about currency, answer could have a dollar sign or not have a dollar sign. You can have 1.0 or 1, all kinds of things like that, which are mathematically equivalent. But if we just compare them with exact string match, we're going to count that as a mistake. And so the answers undergo some light normalization, removing commas and things like that from numbers. And then we parse them using SymPy, and we simplify using SymPy. And we get this normalized final answer and compare it to the reference answer. And so this can also handle, I mentioned a few cases, this can also handle these kinds of minor differences like square root of 1/3 versus 1/√3. It kind of handles simple things like that. And this gives a small boost in the accuracy, where without doing this, we're actually undercounting the accuracy of the model. And so now let me present some more.
I think there was a question in the chat, which was, how do you choose the temperature in the, I think the previous slide?
Here, right?
Yes, that one, yes.
Yes, we did a hyperparameter search over temperatures, and the optimal one turned out to be 0.6, which is, it's kind of in the range where also language models work well just on natural language understanding. It's order 1, and like 0.7 is kind of a common number. For this, we find that 0.6 is slightly better.
Okay, thank you.
Okay, so let me get to the results. So I'll show a couple more examples from each of the data sets, and then I'll show the full results on that data set. And so how much time do I have actually?
20 minutes, but it's a little bit flexible as well.
Okay, cool. All right, so here are a couple more examples. This is from math, this mathematics, high school mathematics question data set. So here we have a line that's parallel to another line, and it passes through a point. What's the y coordinate of the point where this line crosses the y-axis? And this is what the model does. So writes down, okay, this line is parallel to something. It writes down the equation, it picks out the slope, writes down the equation for this line, and then plugs in x equals 0 and gets the answer. So this is considered, this is an algebra, and it's a level 4 question. So the questions are level 1 through 5. So that's, again, just to remind you what these math questions look like. Here's another example that I thought was really cool. So there is a particle moving so that these are its coordinates at any given time, and we're asked to find the speed of the particle. And so this is what the model does. First, it calculates the velocity vector by differentiating the coordinate vector. So differentiate through the sine and cosine. And then it says, okay, we need to calculate the magnitude of the vector. So here's the magnitude. Simplifies, uses cosine squared plus sine squared equal 1 identity, gets 3/4, and this is the answer. So these are two pretty typical questions from the math data set. And here are the results on math. So on the x-axis, we have the different subtopics. In math, we have number theory, pre-calculus, probability, and so on. And then on the right, we have the overall just average over all these different ones. And y-axis is the accuracy. So we have a bunch of different evaluations here. We have the 3 different scales, 8 billion, 62 billion, 540 billion. And let's focus, let's say on the 540 billion model, we have the PALM model, which is the model that was pre-trained on general language, but wasn't fine-tuned yet on the math language. So this is kind of our baseline. And you can see what it does on all of these. And then we have Minerva. This is the model that was fine-tuned on math. And then we sample from it at 0 temperature. So it's like we do chain of thought prompting and so on, but we don't do majority voting yet. We sample from it one time at 0 temperature. And so you can see that here we have the fine-tuning that we did gives a nice boost in performance. This is going from this line to this line, for example. And then when we add majority voting, it can, this fact that we're sampling a bunch of times from the model and picking the most likely answer can boost performance by over 10% in accuracy, which is in these kinds of benchmarks, it's a very dramatic improvement. So overall, with the biggest model and all these different interventions, we get slightly over 50% accuracy on the whole benchmark. And you can compare this to the published state of the art, but also compare this to DaVinci V2. This is the latest language model from OpenAI. We have they have open API access to this model, so we evaluated that as well, and you can see that that model actually does quite well as well. It does better than state of the art results. So these are results on math. Now I want to show a couple of results on MMLU. And again, I'll give a couple of examples just to show one of them. I think this one is kind of cool. And the second one, just to show what kind of examples you can find in this benchmark. So again, this benchmark spans more than math and science. We just evaluated it on the math and science subtopics.
Excuse me, can I ask a question?
Yeah.
You said that you've trained your model on archive papers.
Mm-hmm.
So it basically mostly contains scientific papers, but you evaluate your model on some high school math.
Mm-hmm.
So why does it even work? Because I believe there is not much high school math in scientific papers. And the second question is, what does it do on more scientific things like proving theorems? I don't know, some more advanced stuff like group theory or something like that.
Mm-hmm, mm-hmm. Yeah, great question. So on the first, I think the reason it works is, so kind of half the data set was archive papers and the other half was web pages that contain math. And there are a lot of, pages there with people asking for help on their homework, Stack Overflow math at like many different levels. And so there's definitely a lot in that data, which is elementary school and high school level math coming from this second source. So my guess is this is why it learned to do this. Not probably, I agree that it's probably not from the archive papers. On the question of other and possibly more challenging things like theorem proving, we don't have any results on that. That's definitely something that we're interested in exploring, but I don't have anything to share at the moment. If you have an idea for a data set that we could try to evaluate, let's say group theory on, then I'd be very interested to hear about it.
I think there's another question from Anindita.
Thank you. So my question is that you are training a particular mathematical problem using one solution, but in general, with this kind of problems, there can be multiple solutions. So if you're just using one particular way to train your model, isn't that insufficient to test for different kind of problems?
Okay, thanks. So again, I want to clarify what we are and are not training on. What we're training on is it's essentially unsupervised training in the sense that we're training the model on archive papers and on web pages. We're not explicitly training the model to solve math questions. And in particular, let's say, we're not training it on the math data set. We're not training it even on the training part of the math data set. We're really just asking it questions, like having trained on lots of web pages and papers, we're just asking it questions from the math data set. So we're not biasing it ourselves to any particular way of solving these questions. And we actually see this in practice. If we sample multiple times from the model, it tends to arrive at the answer in a few different ways. It doesn't always use the same chain of thought to get to the answer. Yeah, I feel that that's an important distinction, because often the way these things are done is you take your training set, let's say on math, you train a model on the training set, so it learns something, and then you ask it questions from the test set. That's not what we're doing here. We're just training it on a large corpus of documents, which have nothing to do with the math benchmark, and then we go and ask it questions from the math benchmark without further training. Does that make sense?
Yeah, totally. Thank you.
No.
Okay, shall we take the questions now? Yeah, now or at the end?
Sorry, there was one slide about scaling. What was the scaling in this context? Before, yes, there was a slide about some sort of what. Yes, what is the scaling data? Yes, scaling of what?
So here we're scaling, or they were scaling both the size of the model, so number of parameters of the model essentially, and the amount of data that they're training the model on. So each one of these curves is a model with a different size. So as you go to the right, these are bigger and bigger models. They have more and more parameters. As you go right on the x-axis, this is scaling up the amount of data that they've seen, just in the sense that they've been trained for longer. So the models were trained on more data.
Thank you.
Alex, do you want to ask your question now?
I was just curious about the prompting. So do you just randomly choose prompts from the math data set? I mean, are you using, like, how much dependence is there on the choice of prompts, and are you secretly giving your model? But yeah, I just wonder whether you could be secretly giving your model some information there, or if it's just at least it's only prompting the format of the answer, and if it's the same prompts and all that stuff. Anyway, I think yeah.
Yeah, good question. So on the prompt, the way we chose this prompt is we chose 4 random questions from the training split of math with a couple of constraints. One is that we wanted solutions that weren't too long, because these models, they have a context window of about 2,000 tokens. So we need the prompt plus the question and the answer to fit in that. And so if some of these questions have very long solutions and then they don't fit. So we chose ones where things fit. And the second thing is, some of these questions, they have figures in them, like the geometry questions have figures in asymptote or TXI or one of these, and we didn't include those. But other than that, we just chose 4 random questions from the training set. We didn't tune on the prompt.
Okay, thanks.
Okay. Good. I would suggest unless there are urgent questions, we take them at the end so that we can keep on the flow, and then.
Sounds good. So I'll try to hurry up. I mostly want to get to the mistakes that the model makes, and then I think I can quickly wrap it up. Okay, so on MMLU, maybe I'll skip this example. So these are multiple choice questions. So this is just another example of a question that the model can solve. I think the only cute thing here that I just wanted to highlight is that this is a high school level question. And I think at high school level, you're supposed to assume that G equals 10. So there's a question here about a stone being thrown, and you need to calculate the vertical velocity. And the model puts in 9.8, so it gets this number, but it needs to pick among these different multiple choice answers. So it gets to this expression for the velocity, and then it says, oh, okay, that's kind of approximately 50 meters per second. Whereas if you just put in 10 here, you would get 50 exactly. So that I thought that was kind of funny. And then just to show some of these MMLU questions, they don't require any calculation. It's a knowledge question. So here is when the shadow of the moon falls on the Earth, which is the right choice, and it's a solar eclipse, but the model gets this wrong and it says lunar eclipse. But you also have these kinds of questions in MMLU. And okay, these are the results on the STEM part of MMLU. We get nice performance. I don't have much more to say about this. Okay, so let me show a few examples of the mistakes. So we actually looked at 200 samples where the 8 billion model made a mistake, and we categorized them, and we found that there are some themes and what kind of mistakes the model makes. So about half the mistakes are calculation mistakes, where the model just gets kind of the algebra wrong. So for example, here, the question is, there's a dancer, a figure skater, spins this many degrees, starts out facing north, and then where is she facing when the spin is over? And the model just calculates the remainder. It does the division wrong here. It says it's 360 degree and then 150 degrees, which is not correct. And then there's another mistake, because if you actually spun 150 degree, you wouldn't actually be facing south. So the mistakes kind of compound. But the first mistake here is just a calculation mistake. And I just want to point out that it can make a calculation mistake even if it's not like in a LaTeX block. It can just do that, like it says the answer in natural language and it just gets it wrong. So that's one kind of mistake that we see. We also see about the other half roughly of the mistakes are incorrect reasoning, where it's not a simple calculation mistake per se, but it's a sometimes it's a misunderstanding of a question, but often it's just a wrong logical chain of thought. So for example, here you need to find largest 3-digit number where the product of the digits is 12. So it's already starts out kind of funny. It says, well, this is the largest 3-digit number, okay, and this is the prime factorization, okay, maybe that's useful. And then it says the digits 223 will work, which is not true. That's not the way to get the largest 3-digit number. And then it keeps making more mistakes. It says, oh, we need to put the largest digit in the front, which kind of makes sense, but then it puts 9 in the front. So it gets this like completely wrong. So that's another kind of mistake. And then finally, we have false positives, which is what we call cases where the chain of thought contains a mistake, but the final answer is actually correct. And this happens sometimes. We did an analysis on that as well, and we estimate that to be about 8% of answers that are positive are false positives. So here, we don't need to go through all the details in this example. I just want to show that what the model does. It's some question about finding smallest integer where some number is always relatively prime to some other numbers. And so the model starts out fine. It writes down the conditions as equations. So let's just look at these 3 equations. And then it just says some wrong things. We can cancel out the 6 n terms from each side, which is not true. You can't do that in GCD. And then it doesn't even cancel them out. It just leaves the 6n here on the right side. This is all like, just if you go through this, you'll see it's not true. It's not a correct chain of thought. But then it says k = 5, which is actually the correct answer. So this happens sometimes. So these are like, I think the main kinds of mistakes that it makes that I wanted to highlight. I can skip this. I want to leave some time for questions. The model, it's pretty good at basic arithmetic without any chain of thought. It can also answer some questions that have figures in them. The way this works is that this figure in the question is actually presented in using one of the vector drawing languages like asymptote or TIC-Z, which it's probably seen a lot of either on the web or from archive papers. And so that's the input it gets. It gets the vector instructions for drawing this figure, but somehow that's sometimes enough to actually answer the question. So we look at this figure, and if you go through, it needs to calculate the area of the shaded region, so this and this. And so it manages to do that with a perfectly correct chain of thought. So it can also solve some figure questions, which we thought was surprising. Let me skip this. All right, so let me just summarize. I think there are two main points here. One is that if we scale up models and show them the right kind of data, we can get them to do well on quantitative reasoning questions, including math and science questions at around a high school and like early college level. That's one takeaway. It's just that scale helps with these kinds of questions as well, not just with natural language. And the second takeaway is that with these large models, the inference time techniques matter a lot. So we used few-shot chain of thought and majority voting. There's probably a lot more to explore in this direction. I think we're only scratching the surface of how to make the best use of these large language models, but we already see that the techniques that are out there make a huge improvement in the performance of these models when they're implemented. That's all I had. Thank you.
Yeah, thank you very much for this very interesting talk. Yeah. Please raise your hand for questions and then we can go through. So yeah, let's start with the ones we had previously. So I think Mike Douglas, you.
Yeah, hi, great talk. Let me ask two related questions. Have you tried to develop some sort of confidence score, and have you tried giving additional information in the prompt to see if you can turn wrong answers into right answers?
Yeah, great question. So I think the first question is related to what I think Eva asked, and we didn't do this. We didn't do a calibration calculation, kind of because we, from previous work, we thought that these models are actually not well calibrated. But now there's this recent paper from Anthropic that claims that yes, actually these models are well calibrated when you ask them in that particular way. Like if you have multiple choice questions, you ask them like, do you think it's A, B, C, or D, and not just ask them what the answer is. So we haven't done that analysis, but I think now that we know that calibration does actually work, it makes sense to do that. And the second question of can we get these models to correct their mistakes? I mean, that's an interesting question. I don't have any results to share on that.
Thanks.
Right. Then I think Matt Schwartz was also already earlier. So.
Yeah, hi, great talk. Super interesting model. Very, very impressive from my point of view. It's you know, the future. So great job. I have a few kind of technical questions. Regarding this chain of thought, this prompting, I'm not quite sure how you do that. So you don't train the model for the prompting. You just train it once and for all using archive paper. You start with Palm, you train it using archive and websites and whatever else. And then when you're asking it questions, you force it to give the answer in a certain format, or how exactly are you getting it to do the train of thought without additional training?
We just as the input, we just change the input. Instead of just asking the question, we give the input is question, answer, and then the question. That's it.
But the intermediates, you're asking it to spit out intermediate steps to the explanation. So
yeah, just by showing it, and when I say question answer, I mean question, step-by-step answer, question, step-by-step answer. That's what we show in the input. On some questions, any questions from math, it doesn't really matter. Right. And then we ask it the new question that we actually want the answer to.
You mean that's sort of how you define what an answer is? Is it something of that form?
Sort of. I mean, we have no way to force the model to do this. We're kind of just, all we can do is just kind of point it in the right direction and hope that it picks up on the pattern, and it sometimes does. That's it. Yeah.
Okay. The second question is that it seems to do arithmetic rather well. Do you represent numbers in any special way, or are they just like words for the model?
The one key thing here, which we've seen really matters, is when you tokenize. So many models, when they tokenize, they just learn a tokenization, and then what happens is numbers get chopped up into tokens in kind of a random way. Like if you don't pay attention to it, then 1, 2, 3, 4 could be like a token for 12 and a token for 3, 4, but then 1, 2, 3, 4, 5 could be a token for 1 and then 2, 3, 4, you know, and for the model, that's very confusing. So what Palm does, and we do the same, is that every digit is a token. So when we see a number, we split it up to digits, and every digit is a token. That helps. But still, with this extra training, Minerva does much better on arithmetic than Palm. So it's like the tokenization is important, but the extra training helps as well.
So when you say a digit is a token, that's like a word. It's like a letter of a word.
Yes, it's like a word.
Exactly. So the representation doesn't have any numerical content of it. It's just
no. It's just another vector. Yeah, it's just another vector.
And there's an infinite number of them, an infinite number of possible words.
No,
like
there's not infinite. Sorry.
Yeah. Okay. I think I understand. Thank you.
This model has it's the size of the question here is like the size of the vocabulary, like how many different tokens. This model has about 250,000 tokens in its vocabulary.
So that's the finite number of numbers that it can process. If you give it a number larger than that, it won't be in its vocabulary.
No. Sorry, 250,000 is the number of kinds of tokens. So like hello is a token, apple is a token, 1 is a token. So for the numbers, you have 10 of them. They're like, right, 10 digits. So it uses 10 tokens of the 250,000 possible ones. If you're asking about what's the biggest number we can represent, I guess that's a question about the context, the window size of the model. Like what's the size of the input? The size of the input is about 2,000 tokens. So it's the biggest number we can show it is like a 2,000 digit number.
Okay. Thank you.
All right. So then there's, I think, Anindita has a question.
Thank you, and thank you for the great talk. So in comparison to other models like Paul, what are the specific features in this architecture that lets you read off what are the most relevant parts to process the logical structure of the question, or what is more necessary in the whole question for the logical procedure, and versus which are the phrases or words that are really of no importance at all towards the solution?
If I understood the question right, the question is, what's the difference in architecture?
Yes.
It's the same architecture. It's the same architecture as Palm. It's the same training procedure. The only thing that's different is the data that we're showing it when we're training it. That's really the difference. And then the prompting, but we can do the prompting on Palm as well. That doesn't matter. It's really what we're training it on. The transformer architecture is exactly the same.
Thank you. Then I'm actually confused as to why is it doing better than Paul when it is trying to solve some problem or some question logically, like how is it processing some information, like this part of the information is more relevant for the thought process, like the chain of thought prompt, versus this part of the question really does not matter. How is it doing that?
I don't know, in the sense that I don't have an interpretable answer. Like I don't know how it's doing it, but all I can say is that empirically, what makes it have better performance is that it was trained on more relevant data. So like we kind of intuitively understand that reading archive papers and math web pages is more relevant to solving math questions than reading Wikipedia or general books, right? That's the only answer I know how to give. I don't know beyond that how it actually works, how it actually comes up with the chain of thought reasoning. I don't know.
I see. Okay, thank you.
And Duncan, you had also a question earlier in the chat.
Thank you. Great talk. I'm a little confused though. When you say you scrape web pages, how do I know that the very problem you're showing us as being successfully solved wasn't just verbatim from one of the, a Chegg or many a Stack Exchange or something, that the actual problem was there, or it was very close and maybe just the numbers have been changed, which is often the case with homework problems.
Yeah, great question. So there's no guarantee that that's not the case. And actually, when we started doing this, I thought that we could just kind of rule that out, or at least get a good estimate of how many questions we have in the data set or something like that. This turns out to be a very tricky, actually, problem. This is like looking for a needle in a haystack. Let's say we want to know if this question is in this training set. This training set is so big that when you start looking for questions, you find lots of things that are kind of similar, but actually are not the same. If you go and looking for like exact string matches, then you don't find much. So we did some analysis trying to understand to what extent this is important. I have one example here. One thing we tried to do is we took a bunch of questions and we modified them, either by modifying the phrasing or by modifying the numbers in the question and then propagating that through to the final answer and seeing if the model can still do it. And on average, so this compares accuracy of the original question to accuracy of the modified question. On average, we didn't find that this mattered for the model. Now, of course, it could still be that these questions were memorized and that the model is just really good at adapting to modifications. That could be. But then the question then kind of becomes, well, what is really memorization if it learns something and then can adapt to something else? Is it really memorizing? It's not completely clear. So I don't have a sharp answer to this question. What I can say is that we found very little evidence that any of this was memorized. I guess maybe the strongest evidence we have is that we tested it on the Polish, I think, national math exam, which was translated to English by one of our collaborators who speaks Polish. So this is something that's probably not, and the model was only trained on English. So this is probably not something that's out there on the web in English form. And the model does really well. I think it does about as well as an average student taking that exam. So
I wonder if you could run a plagiarism test on, an automated plagiarism test on the.
That's a good question.
Positive outputs, right? That thing over the 80 gigabytes, whatever it was.
Yeah,
but I do wonder it's certainly in a textbook, right? One provides examples, right? That the student uses as a model, right? And a simple problem would be just tweaking the numbers on it, and then then a little bit, and so that's what we use as kind of methods of learning in higher education and education in general. It's very similar. Anyway, but if that's very, when you say you scrape web pages, it's very different from, there were comments about, what does archive papers got to do with simple arithmetic and stuff, but you also had all these web pages in there and I don't know what they were. So anyway, thank you.
Mm-hmm. Yeah, that's a fair question. And I have all I can say is that when we work with the model and sort of make up questions on our own and ask them, and so and we have, I think, at least one example of that in the paper, it manages to solve them at a level that's similar to what we see on the benchmarks. And so I can say that
write a problem that is independent, that has never been written before, I can tell you.
Okay, but then the question becomes, at some point, I think the question becomes, do we care? Because if it can actually throw any problem, if it can actually answer any problem we throw at it, maybe that's good enough. I don't know. These are all difficult questions, and I don't have a good answer, honestly, right now.
Thanks.
I think Eva is next.
All right. Sorry, I've been asking too many questions, but so interesting. So I was a little confused by the discussion of the largest number it can represent. I mean, doesn't it know about, say, the exponential function or scientific notation? Or, I mean, it must have learned those things. So can't it generate arbitrarily large numbers?
Yeah. I just meant literally, if we want to write down a number in base 10, then it's just, there's this technical limitation of this is the number of digits we can show them all. That's
okay, but it could deal with an arbitrarily large number, it sounds like to me. I guess my other question was kind of relate to the previous one, so sorry to belabor it, but if you, instead of what you did, if you just exposed it to some curriculum and then you did the test coming out of that curriculum, so not the same, knowing that it's not the same questions, is that something where, I don't even know if that should be easier for it or harder for it, but is that a kind of null test you might be able to do with the same model?
Instead of training it, you mean, on this large data set?
Instead of training it on what you trained it on, which was what you said, train it on, the K-12 curriculum in some school system, and then test it on the test of that school system or something.
Yeah.
I'm curious what would happen.
I will bet that that will not do nearly as well. These models don't learn like that, I would say, because when you're showing it this curriculum, you're asking it to predict the next word in the curriculum. So that's kind of what it's learning to do. It's not, I mean, it's kind of speculative. I mean, I don't really understand how this, I don't really understand how it learns what it learns, but I will bet that if we do that, it will not do nearly as well. Let's just say that, because that's not enough data. It's just not enough data to get to this level of performance.
Okay, thanks.
Then Kieran, go.
I have another question. So you said that you generate a prompt with a few questions beforehand, before you ask your question on which you validate. So do you put these questions from the same domain? So basically, if you ask a probability question, you put probability questions beforehand, and does it change? For instance, if I put some probability questions and then asks about, I don't know, algebra, will it change your performance?
Yeah, good question. So no, the answer is we don't match it to the subdomain. So this is, so we have, we match to the benchmark. So we have one prompt for math. We have another prompt for MMLU. That's because the format of MMLU is different. It's multiple choice. So the prompt has chain of thought and then tells it what the right choice is. So that's kind of how it figures out to do multiple choice questions. But other than that, we don't specify to a subtopic. So for example, for the math prompt, we have 4 fixed examples from the training set of math. This is the first one, and then there are 3 more, and we use the same ones on every question from this benchmark, like regardless of subtopic. Maybe if we ask it from a particular subtopic with a prompt, maybe that will do better. I'm not sure, but that's not what we do.
Thank you.
Maisam Barkeshli.
Hi, Guy. Thanks for the great talk. I was wondering if you can have the model generate its own questions, like you can give it a topic and it generates questions, and then whether it could also potentially like rate answers to questions, and then somehow you could set up some thing where it self-teaches itself by generating lots of questions and then grading them.
Yeah, so great question. So yes, you can get it to generate questions. It's actually really easy. So when we ask it to solve questions, we show it this prompt, and then we give it a question, and then we wait for a solution, right? Ask it to, so if we just don't do this, if we just don't give it a problem here, we just say problem, it will generate problems. I only have anecdotal, I mean, I personally wasn't too impressed with the quality of the problems that I saw generate, let's say it like that, but we didn't do any systematic analysis on this yet. It could just be anecdotal. I mean, the questions were fine. It generates some questions and solutions, which seemed just okay, I would say like that. And then on the question of grading and sort of generating its own curriculum, yes, there is a way to grade. There was a paper from OpenAI on training what they called verifiers. You can train a model to try to look at another model's answers and determine whether they're correct or incorrect. And then you can use that as a way to, again, re-rank the answers that you got from the model. So in this work, we discussed one way of re-ranking, which is majority voting. Another way of doing that is to train a model on answers correct and incorrect and have that model re-rank. And so I can say that there's a lot of active work in that direction, because we know that sometimes that works. And then on the question of whether we can have it generate its own training samples, there's another paper from Google called STAR, which does exactly that. It shows a model a bunch of math questions, not these kinds, but like I think simpler ones, I think is the ones they used. More like elementary school level, I think, and then have the model generate new ones and then add that to the training set repeatedly, and that leads to some improvement in performance. So that's another technique that can definitely be applied here.
Thanks.
Right, and Alex, you also have your hand raised.
So thanks, Guy. Super interesting talk. So you were showing a slide earlier where you were sort of testing memorization by looking at what happens if you modify the phrasing of the problem as well as the numbers, and you had sort of strikingly different results depending on whether you modified phrasing versus numbers. Would I be correct in interpreting that? Yeah. So
let me jump there.
Yeah,
yeah,
there it is. So, I mean, would I be correct in interpreting like the very strong correlation with modified framing, but the sort of lack of correlation with modified numbers as meaning that your model has somehow, it knows language, which is not a surprise because you started out with a model that knows language, but in some way it hasn't really understood abstractly what a number is. Because if it did, then you would also see a strong correlation in the slide for the graph on the right.
I mean, yeah, I want to say that. Yeah,
you understand what I'm getting at?
I understand the question. I want to say that sounds reasonable to me, but I also don't actually know what that means because I don't actually know what's the experiment to determine whether or not a model actually understood what a number is.
I mean, isn't the experiment the graph on the right? Like that seems like you've run an experiment where you just changed numbers and you asked whether just changing the numerical value alters the accuracy of your output dramatically. The answer is yes. Whereas if your model understood an abstract representation of what a number was independent of a numerical value, I mean, similarly, you showed a graph of the accuracy of arithmetic results based on the length of the number. And obviously, if you just told your computer, if I tell Mathematica to do a simple arithmetic calculation, it doesn't matter, you know, how many digits the number has. But if I remember correctly, you had some drop off. So I think that kind of gets at the same sort of question, which is that clearly the model is learning a lot, but the way that it's learning it is different from how we learn it, which is fine. But I don't know. I mean, I think, yeah, I don't know if you have any comments on that or if that's.
Yeah, I think that the last comment, I totally agree with. It's definitely not learning like humans do. For example, just to just give a sense of what's going on here. So this is 9-digit addition. And the model, in this experiment, we didn't use any chain of thought. So there's no like long addition or anything like that going on here. It's really just, we have the prompt with a bunch of arithmetic questions, and then we ask it to add 2-digit numbers, and it just spits out the answer, either correct or not. It just spits it out, which it's a bit like, I mean, if I had to do 9-digit addition in my head, I don't think I could get like over 80% accuracy. I have to sit down and write it, right?
But then 9 digits is long enough that it hasn't memorized these. There's no way it could have memorized these numbers.
Yeah, I think there's no way it could have memorized 9-digit addition, but you know, maybe it memorized 3-digit addition and it kind of chains it together in a clever way. I don't know how it's actually doing it. I agree with you that because of the fall off here, it's pretty clear that it's not like it learned to do long addition and then it applies long addition to every addition problem it sees. That's like clearly not what's happening here, right? So it's not like a student learning to do long addition and then kind of knows it once and for all. That's not what's happening. But how is it actually doing 9-digit addition? How much of this is memorized and how much of this it's like working out on the fly? Like, I don't know. Clearly, this is not like how humans do it. I think that's obvious from these results. Yeah.
Great. Thank you.
Okay.
Very interesting.
Yeah, super interesting. So, I mean, there's also on this note, maybe like, you know, children or young kids might not learn in the abstract math way. You know, there's some different learning set. But my question is actually in terms of, again, also scaling it up. So like, okay, we had, you know, high school level, in, you know, beginning undergraduate questions. So the question is more like, you know, how do you envision this, you know, scaling up to, you know, graduate level questions, research questions, etc. Are there some clear thresholds you see that we need to overcome to tackle?
That's a key question here that we won't know, I think, until we try. we don't know how far we can push this. So far, things are still improving with scale, just like we don't have that many scales to compare with, but if we just look at this plot, sorry, I skipped it. We just look at this going from 8 to 62 to 540. Things are still improving. Maybe they're slowing down. I don't know. It's a bit noisy. It's hard to say, but maybe they're slowing down. But there's still room for improvement. We don't know how far scale can take us. And yeah, I don't think we'll know until we run the experiments.
Okay. Good. Yeah. Okay. Okay. So, are these still old raised hands, or are there new raised hands?
Mine is new, if you have time.
Yeah. Quick question, maybe.
Thank you. I hope I didn't miss out if you discussed this already. Have you tested the thresholds on the difficulty levels of theorems that it can learn and apply for questions, mathematical questions or logical questions? Like in number theory.
On theorems, yeah. I don't have any results to share on theorems.
Okay, thank you.
Okay, Duncan, is this a new one or an old one?
Yeah, it's a new one.
Okay.
A little vague. Listening to you describe how, a human gets gets addition, gets it right, and then can do any problem aside from normal human error. And I was wondering about that plot you were showing and the fact that you're using a thermal distribution to guide things around.
Mm-hmm.
As opposed to a phase transition where it's like, yeah, you got this, for this subset of problems. Yeah,
exactly.
And I wondered if there was some way to implement something like that. I guess that's a question.
I'm wondering too. Yeah. Yeah, I don't know how to do that. That it would be fantastic if we could do that, but I don't know how to do that. There's something close we can do, which I don't know, you might or might not consider cheating. We could try to get the model to write code to do that, and then run that code. And then if it figures that out, then it can do any of these problems. To me, that's not
clever.
satisfying.
That's an interesting idea. Yes. Right. To encapsulate and it self-encapsulate the thing. Yeah, that's cool.
Itself, yes. Yeah. If it's self-contained way that I don't know how to do. Yeah.
Awesome. Thanks.
All right. So I think this answers all questions. We had a lot of questions. It was very interesting session. So yeah, let's all thank Guy again for a super interesting talk.